to our video on correlation and causality. Now we've been looking at drawing scatter plots and finding Pearson's R to find out if two variables are related or associated, and we can tell using Pearson's R how closely related they are and how strong the correlation is. Now what I want to talk about is something slightly different, and that's causality. So when we have proven mathematically that two variables are correlated, it doesn't always mean that they definitely cause each other. So causality doesn't necessarily mean, correlation doesn't necessarily mean causality. Sometimes you need to use common sense to help work it out. So I'm going to give you some examples later on of two variables that seemingly completely unrelated, but when you put them together, graph them in a scatter plot and find the Pearson's R correlation, you find that they're pretty strongly correlated mathematically, but we know in real life that they're not. So there are three different reasons that you'll need to be across for why things may not actually be correlated in real life. So the first one is that we might have common response variables. The second one would be confounding variables, which is more to do with the explanatory variable. And the third one is just coincidence. And hopefully that will be the easiest one that you'll be able to get to, because we find coincidence in real life all the time. You'll need to be able to take an example and come up with some examples of response variables and confounding variables and coincidence to decide why two variables might not actually be causing each other. So let's have a look at the first topic, and we've got common response variables. A common response variable occurs when two variables show they are associated because they're both strongly associated with a third variable. So both are strongly associated with a third variable. The example here I've got is if we graphed the number of firefighters at 100 different fires, the number of firefighters who came to the fire, and put it on a graph versus the amount of damage caused by, or the amount of damage caused in the fire, we would probably find that the higher the number of firefighters, the more damage was caused. So if you were just looking at this mathematically and not really thinking about it, you would have observed a correlation. And this is actually, if you do this for real, with real numbers, you do get a strong correlation between the number of firefighters and the amount of damage caused. Does that mean, though, that we can say that the firefighters have caused the damage? Because there's a clear relationship between those two variables, but can we actually say that they're related and that this variable has caused this variable? Hopefully you're using your common sense here, which is what I asked you to do up the top, and you can say, well, no, the firefighters aren't the people causing the damage, hopefully. There is a third variable out here that is impacting on both of these variables, and we call this a common response variable. So what we've actually got is the size of the fire that's a response variable that is causing the number of firefighters. So these two are correlated. Bigger fire, more firefighters. So really the size of the fire is causing the number of firefighters, and the size of the fire is also causing the damage. So there is a correlation between these two variables. There'll be a correlation between these two variables. You'll find a correlation between these two variables if you graph them, but we know that in reality they're not actually causing each other. So that's what we're talking about. Correlation does not mean that one variable has caused another variable. Our explanatory variable has caused our response variable. You need to use your common sense. So common response variable is when you've got a third variable out here that is causing both of these, and it ends up making it look like these two are related when they're actually not. Our second example is confounding variables. This occurs when there may be more than one explanatory variable that causes the response variable. So let's see how that works. If we look at the amount of unemployment, and if we've got high unemployment at a particular time in a particular town, we may end up with increased crime in that town as well. Can we say that, so we've observed a correlation here, and found out Pearson's R, and there is a strong correlation, but can we say that unemployment causes increased crime? That's what we're trying to find out. Using your common sense again, hopefully you can think about it a little bit. And there are a whole lot of other reasons that unemployment may impact on increased crime, but there's probably a whole load of other things going on as well. So we could have, there could be all kinds of reasons for increased crime and even all kinds of reasons for unemployment. So it could be that the economy's in a bit of a depression, it's a bad time, and so that's causing more crime. Could be that people are not as well educated in that town and that's causing more crime. Could be lack of positive influences in the town, positive role models causing increased crime because people aren't really sure what to do. There's lots of negative role models there. It's not necessarily that unemployment is causing increased crime. So these two are correlated really strongly, but that might not be that unemployment is causing increased crime. So this is probably the most common one with the confounding variables, because you're going to have lots of different things that you can think of, and it's hard to kind of split them up to work out which one is actually correlated directly with the other one. Could also be that some of these things are causing the unemployment, which is then causing the increased crime, or any kind of could go in any kind of order. So the confounding variables is when you have more than one and it kind of keeps going around in a circle and you really don't know what's causing what. Common response variables is where you just have a third variable that is causing both of these, and that's related to both of those, and that's why you're getting this correlation that looks like it's correlated when really it's not. Okay, the third example is coincidence. And we use this word in everyday language, and that's going to have the same meaning that we're going to use in maths. So it occurs when two variables are not at all related, but when we graph them and find Pearson's R, they appear to show a relationship. So I've got some examples here for you. These ones come from a website called tylervingen.com, which is written down here, if you'd like to check out some more. And basically he takes these completely unassociated sets of data and graphs them together and tries to see if there's a correlation, and then publishes any interesting ones he finds. So I've copied 3 of them here for you. First one is I've got per capita cheese consumption correlates with the number of people who died by becoming tangled in their bed sheets. So if we look at the graph here, you've got a little hump here, then it goes down a bit, then it goes up again. And these two graphs over time from the year 2000 up to 2009 are really closely correlated when they go up and when they have dips and when they go down. If you put all that data, and he has done this, put it into his CAS calculator or a spreadsheet application to find the correlation, and he's found the correlation. Pearson's R is 0.94, so 94% correlation. So if you were just looking at this data, you would say these two variables are very closely related to each other. But hopefully when you use your common sense, you go, well, how much cheese the country, and this is probably the US, how much cheese the country eats compared with how many people die, cheese is probably not causing people to die becoming tangled in their bed sheets. That's where you need to use your common sense. This is probably the easiest one to do, coincidence, because you can clearly see these two things would not be related, so you can just put it down to coincidence. So they are still correlated very strongly, but there's no relationship, and one variable is definitely not causing the other variable. Second example I've got here is the divorce rate in Maine, which is a state in the US, correlates very strongly with the consumption of margarine in the US. So you can see margarine's going down and the divorce rate's going down. So this would be a negative correlation, but there's a little dip here for both of them, which is really interesting. They're very close together. It starts from the year 2000, goes up to 2009. When you put the data in, you find a correlation R value of 0.99, which is extremely strong correlation. But hopefully when you use your common sense, you can go, well, the amount of people divorcing is probably not related to margarine and the amount of margarine people are eating. Last example I have is consumption of mozzarella cheese. We're getting into the dairy products today, aren't we? In the US, correlates strongly with the number of civil engineering doctorates, which is a university degree. Number of engineering degrees awarded in the US. So again, the graphs are really close together. When you calculate the correlation, you get 0.95 because it's a positive correlation this time, but not related. So you could put this one down to coincidence. Each of these three here would be an example of coincidence, and usually people find that the easiest one to identify when they're trying to find causality. At the bottom here, I've just got a reminder for you. Correlation does not imply causality. Does not imply causality. This is something that you just need to be really clear about. Put it in your summary book so you've got it there. A correlation tells you about the strength of the association between the strength between the variables, but it doesn't tell you whether one variable causes the other one. You need to use your common sense and decide whether it's a coincidence that the two variables are associated strongly, like these three, or whether there might be a confounding variable, a third variable, or a common response. Sorry, common response was the third variable, and confounding was where there are three or four or five or all a whole load of different ones that you can't really specify which one is the variable you're looking for. Thanks for watching the video.